DFCCIL. And we have definitely to go in this direction. Now, next paper is by Irisen Sharat Kumar Agrawal. He has jointly written it with the students from SIT Pune and VSIT Mumbai. So it should be an interesting paper on mathematical basis for optimization of chord to assess surface unevenness of semi and high speed track.
Respected sir, good afternoon. Irisen, apart from imparting training to our professionals and the serving officers, we are also giving internship to young engineers in their final year or second or third year of engineering. The advantage what we are gaining from them, they are energetic with fresh mind and fresh ideas, and moreover they should able to work more mathematical and computer oriented tasks, which at the later age we find little difficult. So I took the advantage of their fresh ideas and their enthusiasm to develop the mathematical modeling for the very basic requirement of any monitoring system. We have, right from the first paper we have seen, we are adopting different chord lengths, but why? And how it can be optimized so that it will serve us well. So this is the theme of this paper. Any unevenness, it is a combination of several waves. It is not one wave, and these several waves has to be looked from the point of view of their wavelength. So rail corrugation and rolling defect, they are having a wavelength of 0.1 meter to 3 meters. Then track parameters for maintenance, that is cant, level, alignment, twist and gaze. They are having the wavelength of 3 meter to 25 meter. Whereas alignment is having a wavelength 25 meter to 70 meter. And wavelength more than 70 meter is mainly required for the correction of the geometry for the initial laying. Waves are superposition of several waves. When we are capturing the data, this amplitude of the wave, some of the waves are getting amplified and some of the wavelengths are getting suppressed. So whatever data we are capturing, it is not the true representation of the track surface unevenness. However, this problem can be avoided if we are using the acceleration based measuring system. Then obviously the magnification should be the basis of selecting the suitability of the chord length. A very beautiful example was given by Aswald, and in that he has given what are the different wavelengths and how these wavelengths should be captured and where we are able to use them for the rectification of the various track defects. In that we can see that the wavelengths which are short wavelength up to 3 meter, basically they are again reflecting the rolling defects like corrugation and the defects of the rail. Then medium length, which is from 3 meter to 20-25 meter, they will be basically related to geometry corrections. One more interesting point here is the vibration frequency of the rolling stock is approximately around near about 1 hertz. So if you are converting that into, then we have to look into the account how the acceleration of the rolling stock is going to give us the real representation of the surface defects. These are the different chords being used by various railways. Indian Railway we are using SONAV, 3.6 meter a short chord and 9.6 meter. This I am talking particularly about the vertical surface unevenness. Whereas in East Japan Railway they are using 40 meter and 20 meter chord lengths. And in one of their paper by Mr. Uno and Ukai, they have concluded 40 meter is enough for even their Shankushan railways. Whereas in Chinese Railway, they are using 30 meter chord and 300 meter chord. 30 meter chord they are using at overlap of 5 meter, whereas 300 meter they are using at the overlap of 150 meter. So by this, both long chord and short chord, what Chinese Railway is using, they are maintaining their geometry in a very perfect manner. Recently, one committee recommended for 9 meter and 18 meter. For that, we will delve one little later. Now, there is one interesting point which has been raised by the Mr. Ono and Ukai in their paper, that the normal tendency what we feel as the longer and the longer cord we use, we will be able to maintain better and better the track. But it is not the case. What they are telling, for longer cord length, the tendency of magnification of measured versine is large for high unevenness, whereas the vertical vibration of rolling stock is not necessarily large at that relevant location. Therefore, longer cord length is not of particular advantage with respect to the ride comfort or the ride quality. So this point has to be seen when we tend to measure the track response based on the ride quality. Now the most common method of measuring the track awareness is by using the versine. As we know, versine is the mid-cord versine. And the way it is being captured, the cord or the two trolleys will be traveling, and in between we are measuring what is the difference between the line of the cord with respect to the rail level. Now, at this point, in the middle unit, this middle unit, it can be as a accelerating device which will capture the local unevenness. Now, this is the advantage of using the modern integrated rail recording, track recording car, where we are able to combine the benefit of cord-based measurement as well as this acceleration of axle. If we are able to combine both the things, then it is possible for us to segregate the local defects and cord or the long wavelength defects, and that will give us predictive maintenance after some sort of regression analysis. Now, the objective of this paper was whether the versine can be expressed as a function of actual surface wave. That means whatever we are doing is okay. Whether the mid-cord versine what we are using is sufficient. Whether the eccentric versine, this is a new concept. If instead of using the sensor unit at the mid of the cord, we are using at eccentric location, whether it is giving us a better result, and what should be the best possible cord lengths. This is a general representation of the cord. In that, we are using mid-cord as well as the eccentric, and then the equation, mathematical equation has been developed for both. This is general equation of the surface wave. This is YA, Y, and YIA is the general expression of surface wave at one particular location which is eccentric. And based on that, if we are measuring the versine, then finally these two are the, at the eccentric location, the surface wave as well as the versine. Here in that we see alpha and beta. These are the parameters which will be totally depending upon the cord length, its eccentricity, and the wavelength. So it is wavelength dependent, it is not depending upon the speed of recording. This is an important point to be noted. Now, magnification factor, I told in the beginning. Magnification factor is quite complex if we are combining all different waves. So we do naturally to simplify it, and the magnification factor at eccentric level will be, eccentric cord method will be the upper one, and at the mid cord it will be very simplified. So far we are using the mid cord method, which is a very simple one. Now, based on this, if we are plotting it, we can see there are three regions. One region is having a very wide base. Another two regions on the back side is having a very narrow base. And if we are not able to select the cord properly, then we may slip into the narrow base and we are not able to get accurate results. Based on these things, now the same plot has been done for the various cord lengths. Here we can see the cord length of 40 meter, it is not able to get the proper amplification factor for wavelength less than 20 meters. Similarly, if you are selecting the cord length of 3.6 meter, then we are not able to get the proper amplification for the cord for the wavelength more than 10 meter. So it gives us, obviously, there should be a two cord. That is what we are doing right now. We are using 3.6 and 9.6 meters. These are the wavebands given for the various cord lengths. What is the efficiency or what is the accuracy? we are combining two cords, then we are able to bridge this gap and we are able to get a better results. Now, if we are using the eccentric cord, then what will happen? What we have seen in the previous case, there was a lot of gaps, what I have shown as reason 1, reason 2 and reason 3. But when we are using the eccentric cord, in this case, the suggested cord length is 0.36 from the center. And in that case, we can see the yellow and the dotted portion, that it is almost covering the entire range with the magnification factor of 0.88 or above. That means we will be able to capture a larger base. And this is the thing, we are using either two cord, 18 meter or 6 meter, or we are using one cord with 18 meter and mid cord and another sensor from 2.52 meter from the end. So that way we can see that we are able to extend the wave band. Now further, the moment we move from here, this will be very useful as far as for the maintenance is concerned. But the second item, when we go for the predictive maintenance, then we must have a mathematical model for the surface unevenness. That medical model has been given by FRA, and they had given in terms of the PSD, that is the power spectrum density, and from there mathematical model can be reconstructed. And if we are using a computer software, then it is possible for us to develop whatever could be a track surface unevenness, and that track surface unevenness can be used to find out what could be interaction between the axle and the track, so that being the track as a dynamic structure, when and where it is subjected to highly concentrated stress, and what are the track components will be stressed and subjected to high fatigue loading. So when we are combining both the two models, then it is possible for us to predict when, after passing how many GMT or after passing how many number of the cycles, our track structure will start crying, or it will be giving us the sign of the defect, it is going beyond its capacity. So what in the very first we have seen two methods of cord based and acceleration based. If these two are combined, then we will be able to make a better decision. These are the references. Thank you, sir. Thank you very much.
Thank you, Mr. Sharad. Now the next paper is by Shri R.K. Agrawal, Shri Vijay Shah and Shri S.K. Asthana on another area, application of wireless sensor network technology on track machines for monitoring and optimization of track maintenance.
Good afternoon, sir. The topic is application of wireless sensor network, WSN technology on track machines for monitoring and optimizing track maintenance. The effective management of rail infrastructure can be done by development of intelligent network, which gives continuous health condition of assets. The key part of the management in future would be condition monitoring of its assets, their defects and deterioration before it causes actual failure. WSN can be used for monitoring the railways structures such as bridges, tracks, tunnels, locomotives, coaches, wagons, etc. This paper deals with the application of WSN on track machines for monitoring and optimizing track maintenance. Very simple approach. Sensors monitor the condition of a structure or machinery. If sensors reading reach a preset or determined values, an alarm is activated. However, this simplistic approach may lead to a large number of false alarms also. For this, sensors are networked and their data processed collectively. Integrated data processing allows an overall picture of an asset condition to be achieved and overall trend condition to be monitored. Each sensor node has radio transceiver, a small microcontroller, data storage for memory, energy source in form of battery. Depending upon the rate of sampling of data needed, above mentioned parts may be of low or high capacity. This monitoring can be used for maintain process tolerances, verify and protect machines, systems and process stability, detect maintenance requirement, minimize downtime, prevent failures, decide maintenance based on predictions of failure rather than adopting a standard schedule or attending after actual failure. This is the typical setup of WSN. We see that here 4 sensor nodes are fitted on the track. From there, data is transmitted through wireless, through Wi-Fi or Bluetooth to the base station, where the data is collected and transmitted to the server.